Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to discuss about the module that is particle size from the paper processing of ceramics. So students, let us see what we are going to learn in this module. First, properties of ceramics. Second, how we can process them. So that is powder processing. Third, green body and its properties. And the last one is particle size measurement techniques and its analysis. So before moving towards the theory of ceramics and its related properties, let's discuss about its history and the origin from where the ceramics have come. The history of ceramics date back to at least 24,000 year BC, where the tiles made of clay have been found in India and Mesopotamia dating back to 14,000 BC. The clay is the most abundantly occurring raw material on the surface of earth, and the ceramic industry was born once the human learned how to mix it with water, shape it and fire it in kilns. No wonder that the word ceramics itself is believed to be derived from keramos, which is the Greek word for clay. So even today, the more familiar ceramics such as tiles, porcelain, sanitary ware, bricks, etc. are all based on potter's clay. However, in addition to these so-called traditional ceramics, we have a new class of ceramics called advanced ceramics, which came on the scene in 20th century as the material system became more refined and spatial compound and processes were developed for structural and electronic applications. So these advanced ceramics can be distinguished in two categories. First is functional ceramic and the second one is structural ceramic. The functional ceramics are the advanced ceramics which we have discussed earlier, used for electrical and electronic, magnetic, optical and related applications, while the structural ceramics are those in which the mechanical properties such as strength, modulus, toughness, wear resistance, hardness, etc. are of primary interest. Almost 70% of advanced ceramics manufactured today belong to functional ceramic category. In powder processing, one starts with a powder of the material to be shaped. Since the ceramics are brittle materials, it is easy to crush and grind them to convert into powders. In the most common technique of ceramic processing, the powders are filled in a die and pressed to the desired shape. Usually, some binders and additives may also be added to the powder mixture. In some cases, a slurry or paste of the powder is prepared, and techniques such as slip casting or extrusion are used to form them into a shape. The process of slip casting is commonly used for the preparation of sanitary wares but can also be used to advanced components. The body produced using the above shaping steps is called a green body. The adjective green comes from the fact that in most cases the body contains some moisture. In the dry pressed articles, the moisture content is very low, but in products made using slip casting or other techniques which start with a slurry or paste, the moisture content is very high. A drying step is to be used in the late case to remove the moisture. During drying, considerable shrinkage of the body may occur. If care is not taken, the high shrinkage produces stresses which can cause the cracking of the body. After drying, the green body is very fragile with a very low strength and low relative density. The relative density is defined as the ratio of the actual density to the theoretical density of the material. For example, if the green body is made of alumina that is Al2O3, the theoretical density is 3.9 gram per centimeter cube. The relative density of green body usually is of the order of 0.6 or less. It is useful to maximize the green density as a high green density leads to a high final density. Often, special techniques such as isostatic pressing and hot isostatic pressing are used to maximize the green and final densities. As mentioned earlier, the green body has a low density, low strength, and is very fragile. So, to develop the desired properties, it is subjected to a firing option in which the green body is heated to a high temperature, usually of the order of 0.7 to zero point 0.8 of the melting point of the material. During this step, a phenomena called sintering occurs. In this process, some grain growth occurs during firing. A properly sintered body has a high relative density as well as strength, which may be more than 0.95. Also, it has high strength and other desired properties. As the relative density is less than 1, there is always some porosity in the powder processed ceramics. Therefore, the final step in the processing may be some grinding and polishing of the sintered body to get the desired dimensions and finish. In some cases, special techniques are also used to machine the body and to achieve the desired steps. The properties of final product depend on several factors, and these includes the characteristic of starting powder, additives mixed in the powder, green body preparation techniques used, and the firing conditions. We will first discuss some characteristics of the powder. This will be followed by techniques of cold pressing, slip casting, and some others to produce the green body. Finally, the processes occurring during sintering and how they control the properties will be discussed, and the emphasis throughout will be on the science of ceramic processing. Amongst various characteristics of the starting powder, the particle size is one of the most important characteristics. It has a great influence on powder flow and handling, powder compaction and green density, sintering temperature, the sintered density, and the properties of sintered products. In general, finer powder needs a low sintering temperature and leads to higher sintering densities, a finer grain size, and an improvement in properties. However, a fine powder is also more difficult to process and may require special processing steps. The range of particle size used in ceramic processing is very large. Usually, the particle size range between 50 nanometers to 1 millimeter, but in some cases it can be much larger, that is a few centimeter, or much smaller, that is a few nanometer. It may sometimes require more than one measurement technique to cover full range of sizes in a given powder. Before moving further, let's discuss some basic terminologies. So first is the relative density. As discussed earlier, relative density is the ratio of actual density to the true density. Next is green density. Green density is the density of green body which has low density and low strength. Next is sintered density. Sintered density is the density of the sintered body having high density and strength. Porosity. Porosity is a fraction of space occupied by the voids. It may be open or closed. Bulk density. It is a ratio of total mass of the body to the total volume of the body. and it includes porosity as well. For example, to calculate the particle size, we have an particle size data which is shown in table 2.1. The particles in a given sample of any powder in general have sizes lying in a range as discussed earlier, that is, they have a size distribution. The simplest way to present the particle size data is to count or weigh the particles lying in different size intervals and give the result in a table or as a figure. Here, the sample powder contains 500 particles. The number of particles lying in different size ranges is tabulated in column 1 and 3. In column 2, the midpoints of the size ranges are given. In column 4, the relative frequency of the particular size is tabulated, while in the last column, the cumulative frequency is given. So in particle size measurement technique, there are several techniques which are available for measurement of the particle size. Choice of a technique depends on the expected range of particle size, cost of the measuring instrument, time available to perform the measurement, and so on. Sometimes two or more techniques may be required to cover the whole range of sizes in a sample. The common techniques which are used are sieving, microscopy instruments, using the sedimentation of particles, and light scattering techniques. So for determination of particle sizes in a nanometer range, the techniques of photons, correlated spectroscopy, or imaging techniques such as electron microscopy or atomic force microscopy, which we call as AFM, are used. So the details of such techniques are not covered in these modules, but these are available in various books. As discussed in previous slide, in figure 2.1, the data has been tabulated and the same data has been figured in figure 2.2. The data in the table is drawn as a histogram in figure A, a relative frequency plot in figure B, and a cumulative frequency plot in figure C. Before doing the calculation for particle size, there are various different cumulative distributions which we are discussing. So the most common method of presenting the particle size data is a cumulative frequency plot, which we have seen in figure C of previous slide. If the ordinate of this plot is multiplied by 100, it becomes a cumulative percent. This plot gives the fraction or percentage of particles finer than a given size and is called CNPF, where CNPF stands for cumulative number percent finer than. If the ordinate is subtracted from 100, then it becomes CNPL plot, where CNPL stands for cumulative number percentage larger than. Depending on the technique used for the determination of particle size, the data may be available as particle diameter versus number of particles, or mass of particles or volume of particles. If the density of all the particles is the same, then the data should be identical whether presented as diameter versus mass or diameter versus volume. When the data is presented as diameter versus mass of particles, say the mass of powder retained on a sieve, then the resulting plots will be CMPF, that is cumulative mass percent finer than, or a CMPL, that is cumulative mass percent larger than plots. The parameters for particle size distributions are mean particle size, variance, and skewness. So, the mean particle size can be represented as mu. So mu is given as mu is equal to summation Ni Ai divided by capital N, where capital N is the summation over Ni, that is total number of particles. Next is variance. Variance is represented as sigma square. Sigma square is equal to summation I goes to 1 to I Ni bracket start Ai minus mu bracket close whole square divided by n minus 1. Skewness. Skewness is represented by gamma, and gamma is equal to summation. Summation goes from 1 to I Ni bracket start Ai minus mu bracket close to power cube divided by capital N, where capital N are total number of particles. Some of the other parameters for the particle size distribution are standard deviation, mode and median. So first is mode. Mode is the size having the highest frequency. Median, the size having 50% cumulative frequency, that is half the particles are below and half above the median. As an illustration, the values of mu and sigma square for the data in table 2.1 are calculated in the next slide, but before moving that, the standard deviation will also be calculated, which is given as sigma and is defined as square root of the variance. Now calculating the parameters of particle size distribution using table 2.1. So using table 2.1, we are calculating the mean first. So as discussed earlier, mean is given as mu. Mu is equal to summation I goes to 1 to capital I, Ni, Ai divided by capital N. So from the table, we can see that it is coming out to be 5.9 micrometers. Using table 2.1, we are calculating standard deviation and variance. So for calculating standard deviation, we are first calculating the variance. Variance is sigma square, and sigma square is equal to summation I is equal to 1 to capital I, Ni bracket start Ai minus mu bracket close square divided by n minus 1. So we can see from the table that sigma square comes out to be 2.266 micrometer square. The square root of variance, that is sigma, is the standard deviation, and it comes out to be 1.505 micrometer for the data tabulated in table 2.1. So we can fit the particle size data using mathematical functions. Very often, the particle size data can be represented by mathematical functions, and the most common such function is the log normal distribution. This distribution is usually followed by powders produced by milling of fine-grained minerals and calcine aggregates. Other functions to which the particle size data can in some cases be fitted are the Rosen-Ralmer equation and the Guardian-Schumann equation. So first we will be discussing about log normal distribution. As mentioned above, in many cases the particle size data is found to follow a log normal distribution. But to understand this distribution function, it is useful to first review the well-known normal distribution. A parameter small x is said to be normally distributed if its relative frequency is given by fx is equal to 1 divided by root of 2 pi sigma x exponential bracket start minus x minus mu x whole square divided by 2 sigma x whole square bracket close, where mu x is the mean, sigma x square is variance, sigma x is the standard deviation of the distribution. A normal distribution is symmetric, and for it, the mean, mode and median all are equal. Therefore, mean, that is mu x, is equal to mode is equal to median for the normal distribution. These quantities are shown on the cumulative curve of the normal distribution in figure 3. Another important property of the normal distribution is x for fx is equal to 0.8413 minus x for fx is equal to 0.5 is equal to sigma x. Here, fx is the cumulative frequency for x. This implies that a fraction equal to 0.6826 of the sample lies within one standard deviation of the mean size. The value of standard deviation is thus easily found by subtracting the value of x for fx is equal to 0.5 from the value of x for fx is equal to 0.8413 using the cumulative plot. Now we come to the log normal, that is ln distribution. In ln distribution, a natural logarithmic of the parameter, that is ln x, is normally distributed. That is, if y is equal to ln x, y is normally distributed. The distribution is given by f of ln x is equal to 1 upon root of 2 pi ln sigma g exponential bracket start minus ln x minus ln mu g whole square divided by 2 bracket start ln mu g bracket close to power square bracket close. The parameters mu g and sigma g are called the geometric mean and the geometric standard deviation. A log normal distribution is positively skewed when plotted as particle size versus relative frequency. The normal and the log normal distributions can be compared, and it is observed that log normal distribution is skewed to the right, that is to the larger sizes. In the cumulative frequency of ln distribution, f of ln x or equivalently f of x is plotted against x, that is particle size, then the geometric standard deviation is obtained. Let's see an example for such calculation using logarithmic normal distributions. So this examples helps to determine the parameters of the particle size using ln distribution. So this is the example of mild bauxite powder where the size and CNPF are given. Assuming that the powder follows a log normal distribution, let's find the geometric mean and geometric standard deviation of the distribution. As you can see from this figure is the plot of particle size d versus CNPF as fraction. The geometric mean mu g is the value of d corresponding to 50% value of the CNPF. From this figure, this is 1.15 micrometers. The value of geometric standard deviation sigma g is obtained by taking the ratio of the values of d corresponding to CNPF, which is 84.13%, and the mu g. Therefore, from this figure, sigma g is equal to 2.85 divided by 1.15. That is the ratio of the values of d corresponding to CNPF to mu g. So the value of sigma g comes out to be 2.48 micrometers. Hence, for the above particle size distribution, the geometric mean, that is mu g, is 1.15 micrometer, and the geometric standard deviation sigma g is 2.48 micrometers. Therefore, using this example and log normal distribution, we can see that we can calculate the parameters of particle size data. So the first equation is Rosen-Ramler equation. The particle size data of some materials follow this distribution. It is given by Fm as a function of A is equal to 1 minus exponential to power minus A by A naught to power M. Here, A naught is characteristic parameter of the distribution, for which Fm as a function of A is 0.37 and M is the shape parameter. The reciprocal of M is a measure of the width of the distribution. That is, if M is large, the distribution is narrow. While discussing the mechanical properties, we will again come across the parameter where it is called the Weibull distribution. So the next distribution is Gordon-Schumann equation. In this, the particle size data of coarse industrial minerals produced by crushing and grinding often follow this distribution. It is given by the following equation, and the equation is Fm as a function of A is equal to A by A max to power n. Here, n is a constant indicating the range of sizes and A max is the apparent maximum size obtained by extrapolation. For this distribution, a straight line would be obtained when it is plotted on a log-log paper. So students, let us summarize what we have learned in this module. So initially, we have started with the processing of ceramics, and the processing of ceramic is mostly carried out using powder processing. The powder is first compact into a desired shape by a technique such as dry pressing. Then the pieces thus obtained is called green body. The green body is first dried and then fired to obtain a completely dense structure. So the characteristic of starting powder have a great influence on a final properties. So one of the most important characteristics of ceramic powder is its particle size distribution. It can be measured using several techniques which we have discussed in this module, and from the data obtained, several parameters of the particle size distribution such as average particle size at given mass percent can be specified. So often it is possible to fit the particle size distribution to standard statistical distribution functions. So in that case, the complete information about the particle size is specified by just giving the parameters of the distribution, which are usually 2 in number, and one of the most common of these function is the log normal distribution function, which we have discussed in this module. From a plot of the cumulative number fraction or the cumulative mass fraction, the parameters of the distribution like the mean, standard deviation can be deduced, which give complete information about the particle size distribution, where several other statistical distribution are also used to fit the particle size distribution data and get the accurate values. Thank you.